In this video, I'm going to give a very quick overview of the variational method. And so I'm going to go kind of fast through this for a couple reasons. And the first is for this molecular orbital playlist, the main thing I wanted to do is sort of bridge a gap getting to what's called the secular equations and the secular determinant, which we will be sort of using in the next several videos. And so I wanted to make sure that there was at least some understanding of where those things came from. Uh, but it's not absolutely necessary to understand the variational method in order to understand what I will be doing in the next few videos. So like I said, this is sort of just bridging a gap. And the other reason is in my quantum mechanics playlist, I'm going to go through the variational method in a lot more detail. And so maybe by the time you're watching this video, I already have those videos out. But as I'm recording this, I have not yet even recorded those. So that will be sometime in the future. But so like I said, I'm going to go kind of quick through this. The lecture notes, which are fairly detailed, will be linked to in the description down below. So if you want to look at this in a little bit more detail yourself, then you can go ahead and do that. Or if my videos are out, you can go check it out in my quantum mechanics playlist. But anyway, without further ado, so we can get into this. And so if we want to know the energy eigenvalue of a wave function, then we can find this here. And so we have the Hamiltonian in there, and we are looking for the energy there. And so we want to find the expectation value for our Hamiltonian here, and so that is the sum of these wave functions here with the Hamiltonian in between. And so this will actually become an integral in the limit. But if we can't solve the time-dependent Schrodinger equation, then we can use this theorem right here, where this EGS is the energy of the ground state. And so these two phi's here are test functions. And so we are using these test functions, and this theorem says that the energy of the ground state will be lower than or equal to the Hamiltonian acting on these test functions here. Or these test functions can kind of be anything, but there are sort of test functions that are used more often because they are known to be at least similar to what the actual wave function will be. So this works because if we express the wave function as a linear combination, so we are adding up these wave functions here, so it's a linear combination of those wave functions. We have that the phi is normalized, and so we end up with this here, and the expectation value of our Hamiltonian will then be this right here. So it's just this up here, but with the energy now in it. And since by definition the energy of the ground state is lower than or equal to any of these other energies, we then have this right here. And so because we said that this up here is equal to 1, so we have that equal to 1, we have that the expectation value of our Hamiltonian is greater than or equal to the energy of the ground state. And so if we want to look at an example here, so we can use the 1D harmonic oscillator. So I do have several videos going through this in my quantum mechanics playlist, so I'll go through this a bit fast here. So we have our Hamiltonian, it looks like this, and so we pick a Gaussian as a trial wave function. So this phi here is our trial wave function. And so we determine this A by normalization, and so we get this, what I have here in red. Then the Hamiltonian in terms of the kinetic energy in blue and the potential energy in green, which is what I have up here. So we find those, so we find this and this, and we find that the The kinetic energy is what I have here in this brown, and then this potential energy is what I have here in this sort of, I guess, lighter brown color here. So this gives us that the expectation value of our Hamiltonian is equal to this kinetic energy plus this potential energy here. And so then we want to find the change in our expectation value as this B changes, because we want to find the derivative with respect to V, or B rather, where it is equal to 0, because that is going to be where we are sort of at the lowest energy. And so we want to find the lowest energy possible, because the ground state is going to be the lowest energy. And so we take this derivative, and what we find is that we have B equal to this right here. So if we put that back into our expectation value for the Hamiltonian, we end up finding this, which, if you have watched my 1D harmonic oscillator videos, you know that this is exactly the ground state for the 1D harmonic oscillator. But in this case, we knew what the ground state was, knew that it would resemble a Gaussian function, but the Gaussian is often what is used even when it doesn't resemble the ground state. And so I'm going to sort of jump ahead to what's called linear variational method, because this is how we will get to our secular equations and secular determinant. So we can express our energy expectation value as this that I have here in the box. So we have this up here with the Hamiltonian in it, and this right here, which is the inner product of our wave functions. And so we have this right here, which we can express as these two linear combinations. And so after we sort of make this definition right here, we end up with this as our as what we have right here. So this is our linear combination right here, where these C's are those coefficients that sort of tell us the contribution of each of these. Then we do the same thing for the denominator of this up here, so that right there, which is what we have here. We make this substitution here, we define this right here, and so we end up with this, and now we, instead of these H's that we have up here, we have these S's up here. And so now we can do this here. So this is just that same equation from above, but now we're putting in those things with the H's and the S's. And so we can rearrange this. And so once again, we want to find the lowest energy, which is the same as what we were talking about above. And so we take the derivative with respect to the C1 here on both sides. So we have this right here, and we have that right there. And so after we do this, we get down to this point here, and so we have this, but then we make these substitutions of our things with these H's and these things with the S's, and so yeah, so we substitute those into there, and after we do a little bit of algebraic manipulation, we end up with this right here. And if we do the same for the derivative with respect to C2, so remember up here we're doing it with respect to C1, but we do it with respect to C2 as well, and we get this equation right there. And so these two right here and right here are called the secular equations. And these can be put into this matrix form like this. So the determinant of which would be that, but we have that the wave functions are normalized. So these S11 and S22 here are just 1. And so we end up with this as our secular determinant. And this is for our sort of our two-state wave function that we are looking at here. But in general, this determinant would be this sort of n by n matrix for n atomic orbitals. And so this right here is just looking at for 2 atomic orbitals, but if we wanted to look at for n atomic orbitals, we would have to do this much longer one. And then so we want to solve our 2D secular determinant. So we take the determinant, which is what we have right here. We FOIL this out and do some algebraic manipulation to get this right here. And so we have this, so we have this e squared, this e, and then we have, I guess, what would be e to the 0 there. And so this is actually a second degree polynomial, and so we can use the quadratic equation to solve for e, and so this is what it would be as the quadratic equation. But we see we have all these h's and s's in here, and those were defined like this, which so each of those are these integrals here. And so we have these integrals here that we would need to solve, so from our definitions above. And so right here I'm just showing that this S is what's called the overlap integral. And so it's the integral that's essentially looking at what is under here, so where our wave functions overlap. And so evaluating all these different integrals can be very difficult, and so it's usually done with computers. And so we can use this example, and I'm pretty much copying this almost exactly from this Chemistry Libre text by Claire Valens. So she goes into a bit more detail here, but all of this stuff, it comes right from there, and so that will be linked to in the lecture notes. And so these values here were obtained using a computer. So we have our H11 is equal to this minus 26, and our H22 is this minus 22.2216, and so on and so forth. And so we can put these into our secular equations. And so when we solve this up here, we get for the E plus this 29.8336 electron volts, and for the E minus with this minus 31.0063 electron volts. So then we want to solve for our coefficients. So our C1 here and our C2, so we're doing it for our E plus and our E minus. So when we put our E minus in there, we have the minus 31.0063 there. So we solve it and we get the C2 is equal to this 1.1265 times our C1. So our molecular orbital psi is this right here, is that linear combination of these atomic orbitals. So then we substitute this in here for the C2, because we know that the C2 is equal to this. And so we end up with this right here, so we can factor out the C1, and we have this right here, which after we normalize to find the C1, we get this right here. And then we can do the same for the E plus, and we end up with this right here. So these two molecular orbitals right there, where the psi1 and psi2 are the bonding and anti-bonding molecular orbitals respectively. So we are looking at this in the ammonia, and so those are the ones with the A1 symmetry. So the atomic orbital psi or phi1 wave function comes from the nitrogen atom, while the group orbital phi2, which is this, comes from the 3 hydrogen atoms. And so if we actually use this, and these are sort of things we will be finding out how to derive in the next several videos. But so we can use these secular determinants then to actually find the energy for these. And so we actually get we actually get this. So this phi1 here is from the nitrogen atom, and then these sort of different looking phi's are from the hydrogen atoms on our ammonia. Then these numbers here are our coefficients. And so we can see that because these are normalized, if we add up the square of these, so we have this squared times or plus 3 times this squared plus this squared minus 3 times this squared, since this has a minus on it, and that has the 0.3837. And so the other 0.6163 contribution would be from these two right here, which like I said, in the next several videos, well, I'll actually be showing how we find those. But I just kind of wanted to show how we would actually use these secular determinants to sort of find the coefficients on these for our molecular orbitals. But anyway, sort of the take-home message, I guess. So these definitions that we will be using here, we will be using in the next several videos. This secular determinant stuff here is important. So like the secular determinant here for our sort of two molecular orbital system, and these secular equations up here. So these are all kind of the take-home message. And so in the next several videos, I'm just going to be kind of jumping right to these. So I wanted to make this video, like I said, to sort of bridge this gap and kind of show where these things come from. But I think, you know, even if you didn't watch this video, the stuff would make sense in the future videos. But like I said, this is just sort of bridging a gap that as I'm recording this, I have not recorded any videos in my quantum mechanics playlist talking about the variational method. And so this, like I said, is just kind of a crash course on this. But anyway, I hope you found this video helpful, and I will see you in the next one.